So as always, some logistics things. I promised you all I would do it, and I did it. I've updated your discussion grades. So remember there was some snafus regarding the grading. So if you posted it in your discussion section and your TA graded it, I have moved that grade over. So that's in the system. I have moved your all's quiz grades to the adjusted quiz grades. Remember I told you they're scored out of, in the quiz thing, there's 5 questions, so it originally scores out of 5, but I adjust that to being scored out of 4.5, so now they're in there. So finally, you all have, in the grade system, you have your discussion 1 grade, and you have your grades from quiz 1 and quiz 2. So that's pretty much everything we've done so far. I wasn't able to move anything else over because quiz 3 is in progress. That's the end of this week. And discussion 2 hasn't been graded by all the TAs, so I didn't move that one over either. I will probably move the discussion grades over sometime around the quiz, right before, like that Tuesday before the test or something, just so you all know your grades are as up to date as I can kind of make it. It's just a manual thing I have to do. Download all the grade books, sort and search, not a huge deal. So, I had some students come to my office hours, which is always wonderful. Please, if you have the time, come on visit me, or you can always shoot me an email. One of the benefits of this was that I saw there were some common difficulties, specifically when it came to the potential problems, and namely the conservation of energy problems. So we've done a few in class, and there were some kind of nuances that I think tripped some people up. And so I'm going to show you all. There's kind of a quick and easy way. All these problems basically boil down to the same setup. So I'll show you all that real quick, and then we'll jump into our stuff with capacitors and resistors. So reminder to you all, I'll continue to emphasize this. I'll put it in all caps. If you see the word speed or velocity in a problem, it's a conservation of energy problem. I've said that a few times, but now it's in writing. If you see the word speed or velocity in a problem, it's a conservation of energy problem for test 1. After test 1, we are going to see speed and velocity with magnetic fields, in which case they won't be, so I'll just add that extra rule when we get to that point. But when we're talking about charges, and we're talking about voltages, and we're talking about speed, if you see speed or velocity in a problem, it's a conservation of energy problem for test 1. Again, when we get to test 2, we're going to see velocity with magnetic fields, and so the caveat, I'll give you the caveat when we get to that point. But for now, this works. The second thing I want to point out to you all is, you may have seen this in Physics 1, but at the end of the day, when we set up a conservation of energy problem, it looks like this. Potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. And we can kind of rearrange this. We can move all the kinetic energies to one side, and we can move all the potential energies to one side. We put a little E here to clarify we're talking about electric potential, but the same logic is going to apply. So I can do this. So potential energy initial minus potential energy final. I just subtracted the potential energy final over. Equals kinetic energy final minus kinetic energy initial. So I just moved them all to the kinetic energies on one side, potential energies on one side. I subtracted the potential energy final over, and I subtracted the kinetic energy initial over. And so you get that the negative change in potential energy. Why is it negative? Because normally it should be final minus initial, but this is initial minus final, so it's flipped, so it's backwards. Equals the change in kinetic energy so the change in potential energy equals the change in kinetic energy with a negative sign. But it so happens that kinetic energy in our problems, in every single one I've given you, basically always ends up being a positive number. And we remember that our equation for potential energy always ends up being Q times V. So at the end of the day, when you are solving one of my problems, they basically all boil down to this equation. QV equals 1/2 mv squared. The reason for that is that in all our problems, our thing either starts at rest or ends at rest. So the kinetic energy, I don't really have to do subtraction. I didn't give you all complex problems. I didn't give you all problems where it's moving at some point and then also moving at a later point. It is either at rest at the beginning or at rest at the end. I could clarify here if we really want that this is technically Q times delta V, but it may just, again, I'm going to just make your all life a little simpler. Remember, whenever we talk about voltage, there's an implied difference. Kind of hold that somewhere in your head. And so for the sake of calculating problems, every problem I'm going to give you boils down to this. Q times V equals 1/2 mV squared. If I give you the voltage in the problem, bam, just plug that voltage in right there, call it a day. If I don't give you the voltage, there's going to be something causing the voltage. Maybe that is a point charge. If I have a point charge, remember a point charge is just, boom, there it is. It's just a charge at a point. If I have for a point charge, I'll just write it down here. So we've done a problem like this where we had to find the potential due to a point charge. So we had two charges. One was fixed in place. Another one was free to move. The one fixed in place makes the voltage, K, Q over R. The other one is the one that is moving. I will draw a picture of that. So for a point charge, let's go ahead. It doesn't matter whether it's positive or negative. I'm going to just make it positive just for the sake of simplicity. It does not matter. We'll call this one Q1. We'll call this one Q2. This one would be the one fixed in place. Fixed in place. This is the one moving. So if I did that, just to clarify, I need the V1, charge 1 is making the voltage, charge 2 is the one that gets the kind of energy from that voltage. Just want to specify that. We've seen a problem like this. It was like the first one I solved with you all, was the how much charge do I need to place somewhere to make something reach the speed of sound. You can look back on that and see how I solved that, but it boils down to this. Yes, sir?
Would the Q that we use in the voltage equation be the same one that we use for the potential equation?
That's a great question. Are these the same Q? And the answer is no. The Q here, the one that, if it is a point charge making that voltage, the Q here is the one making the voltage, so that's the one that's fixed in place, and then this would be Q2, the one that's moving. So I hesitate to put a 2 there just because I don't know if that's going to throw people off. I will put an arrow here to specify Q is the moving charge. That may help us out. This Q is the moving charge, whatever that may be in the problem. The other Q is, if there is another Q, if there's another Q, we get the voltage from that, and we do that. So that's pretty much the problem that I've given you, is either have 2 point charges, and they repel each other, and you can kind of find velocity using conservation of energy, or I just say, hey, here's the voltage, you just, bam, slap it in that problem, call it a day, plug and check. So I wanted to quickly show you all that. Yeah, yes, sir.
Could you explain the difference between electric potential and electric potential energy?
Yes, sir. So electric potential and electric potential energy. Electric potential energy is the energy something gets from a potential. The analogy I like to draw is gravitational potential energy and height. Height is kind of like your voltage. I can have a height, but I don't have an energy until I place something there. So height is kind of like voltage. There's like a potential for something to happen, but nothing's going to get energy until I put a thing with mass there. So potential energy means that there is an actual object there, a charge that has that energy stored in it. Voltage is the possibility for something to get that energy. Just like height. I can measure the height here, but there's no potential energy where my hand is right now, because there's no mass there. There's nothing with mass. I have to put something there to get that energy. So voltage is the possibility for there to be energy. Energy is energy. At the end of the day, when you're solving problems, here's the mantra you can follow. If it doesn't say the word energy, it's not energy. If it doesn't say the word energy, it's not energy. So if I say potential difference, that's V. If I say potential, that's V. If I say electric potential difference, that's V. The second I say potential energy, now it's energy. If you don't see the word energy, it's not energy. And again, the best analogy I can make is voltage is like height, potential energy, electric potential energy is like gravitational potential energy. It's a weird idea. What is energy? Energy is the potential for it to do something. So I need a height difference, I need this voltage difference, and I need to put something there to get the energy. It just takes some kind of wrestling to get there. Yeah.
So just to recap, electric potential energy, energy you gain from potential.
Yes.
Excuse me. Voltage possibility to obtain that energy.
Yes. Yes. Voltage is the possibility that once I put something there, now I'll have energy because of that. But if nothing's there, no energy.
And electric potential energy unit will not be V because potential's in the word.
Yeah. Because energy is in the word. So if I say potential, the unit is volts. If I see the word energy, it's joules. If you see the word energy, it does not matter what is in front of that word. Gravitational, kinetic, thermal. Who cares? If it's energy, it's joules. All types of energy.
Even electric potential energy is joules?
Yes. All energy is joules because energy, the concept behind energy is what the universe started with a set amount of energy. We can't destroy it, we can't create it, but it can change forms. Sometimes it's an electric potential energy, sometimes it's gravitational potential energy, sometimes it's kinetic energy, sometimes it's thermal energy, sometimes it's light energy, but it's all energy. It just looks in different forms, and I can change it from one type to the other. Yeah, good question. Okay, so good stuff there. If you have more questions about this, please shoot me emails, come in the end of class. Voltage is one of those topics that mathematically, we're not doing anything crazy here. We're not doing any vectors. We're not breaking things down, but conceptually, it throws our minds for a bit of a loop. And the better you understand voltage, the better prepared you're going to be for the next 3 or 4 weeks worth of content. Everything builds. So when we talk about circuits especially, if you don't understand voltage, you may still be able to do the math in those problems, but it'll just be easier if you understand it. If you understand the concept, everything else is easier. So jumping into today's stuff, so let me just give you kind of the main points we talked about. We talked about capacitance, and we basically said we can build something that stores charge. 2 parallel plates, we can store charge on it, just like a bucket can store water. These 2 parallel plates can store charge, equal and opposite charge on each end. It is purely a geometric property. We said capacitance was epsilon naught A over D. So capacitance, we could calculate as just epsilon naught A over D. Area of the plates divided by the distance times this dielectric this permittivity for space. We can calculate the energy from 1/2 QV, and we can use that equation C equals QV to write it in 2 different ways. We have all those equations down, hopefully. And then we did 3 problems where we said what stays constant. And we found that if you're connected to a battery, the voltage of let's just kind of quickly show those problems again, just to remind you. We said if you're connected to a battery, voltage of the battery equals voltage of the capacitor. Doesn't matter what I do to that capacitor. Make the plates bigger, make the plates farther apart, doesn't matter. If you're connected to a battery, it gets the full voltage, it gets the full tension. We said if you disconnect it from the battery and you change the geometric properties of it, well, it doesn't matter. What stays constant is the charge. If we change the geometric properties, we're changing capacitance. We're also not changing voltage. Because remember, this is a bucket that stored a bunch of charge. If I disconnect it from the thing that filled it up, it's still got the same amount of water in it, the same amount of charge in it. It doesn't matter if I separate it or whatever. And we said capacitance is the same no matter where my thing is, no matter how much charge is on it, who cares? And the easiest way to think about this is if I buy a 1 farad capacitor from the store, I don't care what it's been used for before this. I don't care if someone used it in 1,000,000 circuits. I don't care if it's shipped from China. It should be a 1 farad capacitor. No matter where it's been, no matter what it's been connected to, at the end of the day, it's a geometric quantity. And as long as no one blew up that capacitor, it's still 1 farad. So that's the 3 kind of things that stay constant. All right, so there's just one more thing we got to talk about with capacitors. It'll be a pretty simple addition to it. Conceptually, maybe it's a little weird, but problem-wise, it doesn't really make things too bad. Up to this point, we have imagined that our capacitors are filled with nothing. The void, vacuum, space. Absolutely nothing is between them. And that's why we've been seeing this. So in the void, in space, we've been using epsilon naught. And I haven't really defined, so that term is called the permittivity of free space. Key word there, free space, vacuum, nothing. And we're not going to get into this too much, but permittivity means how easy or difficult, depending on your perspective, half full, half empty, how easy or difficult it is to make an electric field somewhere. So epsilon naught is how easy or difficult it is to make an electric field in empty space, nothing around. Well, I mean, we can put something in it though. We could put some material, we call it a dielectric. We want that thing to be an insulator. If we make it a conductor, our capacitor just turned into a wire, and what was the point? We got to keep those charges separated. If we put a conductor, they can move from one into the other, and that defeats the purpose. So this dielectric is an insulator. It's an insulator, and it is going to allow us to store more charge. The dielectric is going to allow us to store more charge. I will explain very briefly. There's not going to be any conceptual questions that are going to really pop up on this, so don't let it stress you. But I do want to mention it because it is important. Our real-world capacitors don't have vacuum, they have a dielectric. If you look at my picture, we've talked about this. This does relate to something we've talked about. We said if you put an insulator near some charges, in that insulator, my charges can move. They can move a little bit. So if my plate over here is positive and my plate over here is negative, the positive plate is going to attract some of these electrons. They're going to get pulled in that direction. And if they get pulled in that direction, I'm left over with some extra positives on this end. Why does this matter? Because if we notice, we kind of have a backward situation here. My original field was pointed from the positive to the negative, but inside of it, I have some charges that are making a field in the opposite direction. And because they're opposite, they kind of cancel out a little bit, which, long story short, lets me put more charge in my capacitor. It lets me put more charge because this charge inside kind of cancels out the effect of some of this field and lets me kind of chalk more charges on it. So the net electric field goes down a little bit, which means the potential goes down a little bit. And if we remember our definition of capacitance, our voltage here is in the bottom. So if this is getting smaller, capacitance is getting bigger. So we can put a dielectric in. It lets us put more charge in the capacitor. That's what I want you all to just take away. At the end of the day, what's the only change in the equation? I told you all it's pretty simple. Bam. If you put a capacitor, there's something called the dielectric constant. It's called kappa. That is not a K. That is a Greek letter kappa, lowercase kappa. It is just a constant for materials. If I have Teflon, it's 2.1. If I have Mylar, it's 3.1. If I have paper, it's 3.7. Pick a material that's an insulator and it's got a dielectric constant. Notice for vacuum, it's 1. For space, it's 1 because it doesn't change anything. 1 times that gets you the same thing. So if I have a dielectric constant, I have a capacitor. Great, I made it. I calculate its capacitance. C equals epsilon naught A over D. Fantastic. I put a dielectric in it. What's my new capacitance? Just multiply it by the dielectric constant. We'll do a problem today where you get to see that. It's fairly simple though. You just multiply your capacitance by that. There's only one problem in the problem set like this. It's not a hugely important, it's a minor concept, but I do want to practice it just so we can understand. Because it is important. The real world capacitors are filled with vacuum. They are filled with something, so I want you all to see that. Because at the end of the day, what I'm teaching you should match what actually happens in the world. All right. And these capacitors are kind of interesting because this is more engineering than physics. Capacitors are a real world device that we have generated for a useful function. You will not, lightning clouds are capacitors, and that's basically the extent of it. So I am kind of introducing you to a real world thing that we've built for our purposes, which gets into the fringe of engineering. All right, so let's do some capacitor problems. The second one is going to have that dielectric constant. So we'll explore that when we get to it. It's the only problem in the problem set that has the dielectric constant, so I'll solve it in front of you so that we don't have to worry about too much. But we'll do a quick problem with capacitance, and then we'll get to resistors and see how far we can get. Good news is, even if we run into kind of next class, the next thing we're covering is super quick. So next week's content is super quick, so that's perfectly fine if we don't quite finish everything today. All right, so in open heart surgery, a much smaller amount of energy will defibrillate the heart. What voltage is applied to a 5 microfarad capacitor of a heart defibrillator that stores 36 joules of energy? Find the amount of stored charge. This is almost one of the most classic plug and chug kind of problems. I could draw a picture, but there's a capacitor. That's kind of the extent of the picture I can draw. Not every problem has a picture, and if you really want, you can make up one, but this problem, drawing a picture, doesn't necessarily help us. There's not really anything moving or anything building up, so let's just go ahead and jump to step 1. What is given? We have this 5 microfarad, and this is where the units will help us. We may remember, I'll give you all a few seconds, see if you can match the variables to the units. I'll write down their variables, so we're going to put them here. But what unit do they go to? What variables, that's a better way of putting it, what variables do these match with? What does farads match with? What does joules match with? Give you a few seconds to think of that for yourself. I'll do the unit conversion to regular old farads while we're here, in case that may help. All right. So, if we look through our notes, we may recognize that farad goes with capacitance. You see farad, it's capacitance. The units tell you what it's measuring. We just have to remember, I say remember, we'll put it probably in our notes during the thing. Farad is capacitance, and joules, we said this today, joules is always energy. In this case, when we talk about capacitors, it's the energy stored in it, which is a potential energy. So that's U. So we can move on to step 2. There's no other numbers in our problem. If we end up needing more numbers, we can always come back and investigate. But what are we solving for? It says what voltage? What voltage? So V equals question mark. Step 3, we just find the equation that relates these. And so this is where we need to choose our energy equation wisely. There was 3 different energy equations. One of them has C and U. So we just got to look through that list. See, again, give you all a few seconds, see if you can find that one. It was a handful of slides, 10 or so slides back. I don't know the exact number. I myself will go up and quickly look at it so I don't have to derive it. I just remember that U equals 1/2 QV, and that is not the one we're using. I would end up having to derive it, but I'll save myself some time and just use my notes. The beauty of notes. All right, so we scroll. Energy stored in a capacitor, bam, there's 3 different equations. In our problem, we have the capacitance, and we're solving for the voltage, so we choose the second one, because this has what we have. You always choose the one that's got the variables that you already have. Don't make your life harder. So we're going to use U equals 1/2 CV squared. U equals 1/2 CV squared. Step 4, plug in the numbers. U is 36, 1/2 is 1/2, capacitance is 5e to the minus 6, and V squared. So V is going to be multiply the 2 over, divide by the 5e minus 6, square root the whole thing. You know, I'll leave this squared. I won't do all the algebra in one go. 2 times 36 over that 5e to the minus 6. And then I simply square root both sides to get rid of that squared. If I'd wanted to, I could have solved for it over here. V equals square root of 2 times U over C, and you'll see that's exactly what I ended up doing number-wise. Honestly, doing it with the variables is a little nicer. It's a little easier to keep track of. You don't have to write as much, but I'll put it both ways. Plug and chug, and we'll get some beautiful number. 2 times 36 divided by 5e to the minus 6, square rooting all of that. And we get a very large voltage. We get a voltage of 3,794 point, I can't fit all of that and put the units. As I am writing this, I haven't maybe harped it into your all's head as much as I should have. Don't forget your units, don't forget your units, don't forget your units. So when you are solving these problems, when you're doing the problem set problems, make certain that not only are you getting the right number, you are getting the right unit. Because on the test, I have made problems where the correct answer is listed twice, but the unit is different. So it'll say 12 volts, and maybe, or let's say in this problem, one of the answers may say 3,794.73 volts. One of the other answers will say 3,794.73 joules. Make certain the unit you're putting is the right one. That is an important skill, because if you put the wrong unit, then you're saying the wrong thing. If you like someone said, hey, here's $500, and instead they gave you 500 jelly beans. Stupid example, but it gets the idea across that there are drastically different things if you don't use the right unit. The unit says what it actually is. Without the unit, a number is meaningless. Literally meaningless. If I told you I had 3 what? You have to put a unit for it to mean something. You have to put the right unit. So it means the right thing. All right. So, pretty straightforward problem. The next one says, we have one more step here. There's 2 steps to this problem. Find the stored charge. At this point, we have everything we could possibly want in the world. We have all the variables. We are going to need another equation, so let's copy all this over. So part B, we're going to use all our beautiful work. And honestly, you could have gotten the stored charge even without that. But what's the equation for stored charge? C equals Q over V. When we talk about capacitors and you hear the word charge, just jump to that equation. So we could have chucked that in equation 3, but now we know we need it because, let's go ahead and put that, we need Q as well. So C equals Q over V. We have C, we have V. Let me go ahead and solve for Q. So Q equals CV. Just multiply that V over. And that is going to equal 5e to the minus 6 times our 3,794.73. And we get a fairly good amount of charge. Where's my E? So 5e to the minus 6 times 3,794.73. Yeah. Equals 0.189. I'm just going to round it at this point. 190 coulombs. Boom. And you can always go back and double check your work. Take that, divide it by the voltage, see if you get C. Please do that. When you all have your test, my goal in the design of the test is that by the end of the test, you're not working to the wire. I will try to design it so that there is some time, if you're kind of being diligent, you have some time at the end to go back and check your problems. To go back, to re-plug the numbers in, make certain that it is actually the right answer. I guarantee you, if you have that time and you spend that time, you will probably catch a mistake somewhere. Yeah. Yeah, that's right. Good, good, good. That's why we check our work. Fun fact. That was on my calculator, but I wrote it down wrong. Just goes to show you how easy it is to make these stupid little mistakes. I literally had it right in front of me and I wrote down the wrong thing. So, if I can make stupid mistakes like this, we all can make stupid mistakes like this. We're all united in our ability to make stupid mistakes. Yay, humans. Double check your work, be careful. The good news is, on the quiz, or on the test, there won't be an option that's 0.19. So that will be an indicator that you did something wrong. So one of the beauties of multiple choice is if your answer is drastically different from any of them. And when I say drastically, this is also a good thing to note. So you will not see an answer on the quiz that would be like this. That would be that close to it. I will not give answers that close. They will be, if I give another answer, it will be something drastically different than that one. So if your number is very close, say you instead got 0.0 in my case, 188. Let's say you got 0. That's really, really darn close. If you're within like a rounding of it, that's a good sign. All right, let's go ahead and do that dielectric one, and then move on to resistors. So, how much surface area is necessary to make a capacitor with a capacitance of 1 farad, assuming we have a gap of 10 micrometers and are able to maintain a vacuum? I think I can solve this all in one thing here. So, same old, same old. I'm going to kind of move through this a little quicker just so we can get to our resistors. I can make my beautiful picture. There's my parallel plates, and basically I'm trying to find that distance between them. What is given? We have our 1 farad, that's capacitance, just like before. We have 10 micrometers, which is the gap between them. So that is a distance, that's the distance between them, 10e to the minus 6 meters. And that's all it's given in the first part. Yes, the next one, let's go ahead and add that. We have a dielectric constant of 5. We are not going to use that till part B though. So we got to be careful. Do not put that in. And it's just a constant because it's a multiple. So we'll put that for now, but we're not going to use it in part A. Because in part A it says we have a vacuum but I'll put it now just so that when we get to part B later, we can solve for that. It is saying how much surface area, so we're solving for area, equals question mark. Step 3, what's the equation that relates capacitance, distance, area? We only have one. Capacitance equals epsilon naught A over D. It is a simple plug and chug problem. I'm going to go ahead and rearrange for A. I guess I can do that in, I don't know if it matters where I do that. Sure, let's do it in step 4. So C equals epsilon naught A over D. How do I get A by itself? I'm going to multiply the D over. I'm going to divide by epsilon naught. So A is going to equal D times C over epsilon naught. I multiply the D over, divide by epsilon naught. Whenever I'm doing these algebra steps, if you're ever like, how the heck did he do it? Try it yourself. Outside of class, spend a few moments. How did I get from that step to that step? It'll help strengthen your algebra skills. View it as a kind of little extra exercise, which may not sound fun, but you will benefit from it. And you know what it should end up being. So then we just plug in the numbers. Now that we've kind of solved for our variable, makes it a little bit nicer. 10 e to the minus 6 times our capacitance, which is a nice 1, divided by epsilon naught is 8.854 times 10 to the minus 12. What a horrendous number. But it is what it is. The universe does what it likes, whether we like it or not. And it just so happens that this is what this constant is. You may be wondering, where did that constant come from? Measurements. That sounds stupid, but whenever we give you a constant in any physics class ever, and you look at it, you're like, wow, that's a number, that's a gross number. It came from physical measurements. Remember, physics is our understanding of reality. So whenever we have these constants, we made these equations, and these constants just basically make the math match reality. So they do a measurement where they say this should be 1 farad, so they assign an area, they assign a distance, and then they do the math, solve for epsilon naught. And people's jobs are, some people spend their whole life researching how to get more accurate decimal places to that. That's a really common one with the speed of light. How many decimal places can we be accurate to that? So there you go. Promising future for you all if you want. Go measure some constants. Precision science. All right, 1.13 e to the 6 meters squared. Our unit is meters squared because it's area. Again, units are important. That is that is very large. You should look at that number and say that's a very big area. And then you may question, does that make sense? That's let's see, let's move those decimal places. That is, I don't want to make a mistake, so I literally put it on my calculator in front of me. That is 1,000,000 kilometers by a million meters squared. 1,000,000 meters squared, that's quite big. And this just proves the point. 1 farad is really big. 1 farad is a huge capacitance. So, proving that point to you all. Now the question is, remember in the real world, we do not use vacuum in our capacitors. We use dielectric, and so let's see what the effect of that dielectric. If we put a dielectric with a constant of 5, let's see how much it helps us make a capacitor that fits in a smaller space than 1,000,000 meters squared. So we'll make a new slide, copy all this over, and it'll be fairly straightforward. At this point, I'm going to show you all in a couple ways that we can kind of approach this. So step 4 says, or part B says, what are we solving for? What would our area be if kappa was 5? What's our area 2? We'll call this first one area 1. Let's call the second one area 2. How am I going to do this? We are going to do a beautiful ratio problem. Just to show you where this is coming from. So our original capacitance was epsilon naught A over D. That was the equation for it. Epsilon naught A over D. Let's go ahead and clarify A1, because it's got negative 1. Remind ourselves that, well, let's put our second one here. Our second capacitance, therefore, is epsilon naught A2 over D. And this may be a good time to point this out. I didn't have it explicitly in the equations before. I'm going to show you how I get this. We just throw a kappa in front of it. How did I know to do that? How did I know to put a kappa there? We haven't seen that equation. That's because C, our new capacitance, equals kappa times our original capacitance. Let's go ahead and write it in terms of that. This is the equation you did see. So literally all I did was I put a kappa in front of the original one. Put a kappa in front of the original one, in which case I should actually leave this as area 1, which is maybe going to throw some of us off. That's all right. I'm okay with it. So maybe this new equation is maybe a bit extra for us. We need to get that. We need to get that in the form this. We want to get it to this form because then we're happy. Then we can get A2. We want to get it to that form. These two are equivalent. C2 equals kappa times C1. We know that C2 is epsilon naught A2 over D. So, cancels, 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 cancels. So we get kappa area 1 equals area 2. And therefore, my area 2 is going to be, oh, did that not work out the way I so desired? All right, our area 2, oh, that's not good. My apologies, y'all. I threw that for a loop. The way that worked out did not work out the way it should have. Let's just stick with this original equation here, and that'll make our life a little easier. My apologies, y'all. At the end of the day, my area is going to be 1/5. My area is going to be 1/5. I'll clarify that to you all here. My apologies with showing you all that. I'll look over it later and clarify in an email or something. What does A2 need to be so that I get to my original capacitance? Because C1 equals C2. There we go. That works out better. At the end of the day, I want C1 to equal C2. There we go. My apologies on that little mistake there. So this is my new one. We got our kappa, epsilon naught A2 over D. We want C1 equals C2. When we do it now, we're going to get that beautiful answer that we were so hoping for. So we're going to get epsilon naught A1 over D equals kappa, epsilon naught A2 over D. Now everything cancels. Bam, 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 bam. So we get A1 equals A2 times kappa. The same capacitance. The right one just got that kappa in front of it because we saw that before. We could just multiply by kappa. And now we get A2 equals A1 over kappa, which is just A1 over 5. Long story short, I'm not going to even plug in the numbers. It's 1/5 the area. That's what I want to show you all. So very simply, a lot of math to just show you that whatever the dielectric constant is, it basically multiplies whatever your capacitance is, makes it that many times bigger. So if I had my original area in this problem, if I had this original capacitor, and I put this dielectric, this massive dielectric, because this thing is massive, in there, it would have made the capacitance 5 times bigger. The dielectric multiplies your capacitance, which by extension means you need that much less of the area. Again, don't let this stress you all too much. I promise you this won't come up with the test. Shouldn't come up. I'll double check the quiz. I'm pretty darn confident it doesn't show up there as well. But if it does, the end result is that the kappa reduces, either increases your capacitance by that amount or reduces the amount of area you need by that amount. Same thing. Yeah.
Where did we get that 8.8 figure for epsilon naught?
That's just the value of it. All the time. Yep. Anytime we have a constant like that K, 99, always 99. Anytime you have epsilon naught, 8.854 times 10 to the minus 12. I think those are the only two constants we've covered so far.
So is that, do you put constants on the exams at all?
It'll be on your formula sheet. Or it'll be on that little thing. I'll probably also put it on the test. Yep. You do not have to have that memorized. Honestly, you'll probably have it memorized after doing enough of these problems, but not because I made you. And you won't need it. Okay, so let's move on to kind of more of the meat, not get too hung up on this thing that isn't going to show up too much and isn't a huge deal. Resistance. Okay. Before we get to resistance, so we're kind of turning a new page. The way I've structured the content so far is we're building towards circuits. We are building towards things that go in circuits. Circuits are something where you have a voltage, you have some wires, and you have some stuff in it. What is that stuff? You can put capacitors and you can put resistors. So we're going to build these useful devices that allow us to phones, computers, lights, literally anything that electricity runs through. So we need to understand what electricity is, and to build towards that, we're going to talk about the things that go in the circuit and the properties they have. One of the properties things have is resistivity. And resistivity is the property of a material to resist the flow of electrons. This is a material property. We have a beautiful table here where, depending on the material, it has that resistivity always. Just like you asked about that constant epsilon naught, these are constants. The good news is you don't need these written down. In a problem, if I tell you you have a copper resistor, I will say resistivity of copper is 1.68. I'm going to go ahead and warn you that every now and then I'll have, instead of 1.68, sometimes it'll be 1.7, sometimes it'll be 1.72. Long story short, you do not need to have these written down. You do not need to have these written down. If there is a problem where you need resistivity, either I will give it to you, or it'll be what you're solving for in the problem. So you do not need these resistivities. I purely put them here to show you that it does not matter how much silver you have. It has this resistivity. This is a property of the material. It has nothing to do with the dimensions. It does have to do with temperature. It does have to do with temperature, and we'll look at that in a little bit. But it is purely based on what the material is made of. Kind of a chemistry kind of deal here. Based on what it's made of, how did we find these measurements? Literally, there's a lab, they took measurements on it. That's it. Getting this theoretically would be an absolute nightmare. And once I explain what it is, you'll see why. So for now, all you need to know is what the idea resistivity, property of a material. Does not matter how big or small, kind of like density. Density doesn't matter how big or small your stuff is, it's just a property of material. What is it? What is resistivity? Let's first introduce that idea. Why does this happen? Why do things resist it? So we're going to learn when we get to current, which will be next week, we're going to learn that when you have a wire, it is full of electrons. And we build wires out of metals. So you may remember this idea of a sea of electrons. That metals are conductors and therefore have the sea of electrons. Literally just electrons that are floating around randomly inside of a metal. They're going this way, they're going that way. They're floating around all over the place. Electrons. Once I apply a voltage, aka a battery, it is effectively the same thing as, imagine instead of these being electrons, they're marbles on a flat table. So they're just kind of there. They can wiggle around a little bit. When I apply a voltage, it's as if I took one end of the table and lifted up. Remember, I compared voltage to height. Take one end of the table and lift it up. And what are all these electrons going to, or what are all these marbles going to do? They're going to move. They're going to roll. They're going to roll towards the end with lower potential energy. So we can almost think of tilting this thing. If we have a high voltage, now this will be a good reminder. Let's say we have a 9-volt battery. One end it's 9 volt, the other end it's 0 volt. I'll remind you, give you a second, this will be a good review. Which way are they going to move? See if you remember. Are they going to move towards the 9 volts or the 0 volts? These are electrons. Will they move towards the 9 volts or the 0 volts? This is a good thing to kind of jog your brain on. You got a 50-50 shot, if nothing else. All right, if you said towards the 9 volts, you were correct. Electrons, negative charges, will move towards higher potential, which we reviewed was lower energy still. Anyway, they're going to move. They're going to want to move and groove. But this wire is not an empty space that these things can just move through willy-nilly. It's not a void. It is literally a metal. And that metal is full of atoms, nuclei, which each have their own electrons on them. It is full of these things. And so at the end of the day, when these electrons are moving through this wire, they are bumping into atoms. They're bumping into atoms, and they're bouncing off these atoms. So if I actually drew the path, and I'm going to use a red arrow for this. If I drew the path one of these electrons took, it would look all sorts of crazy. It would go this way, then this way, then this way, then this way, then this way. At the end of the day, it's mostly moving to the right. But you can almost think of it like a pinball game. A pinball game is ultimately sloped, so it goes to the bottom. But on the way there, it may bounce off a bunch of things. But at the end of the day, it will get to the bottom. And the pinball machine will ultimately get to the bottom, no matter how many things it bounces off of. This is resistance. Different materials, it's easier to go through. Some materials, it's really hard to go through. Why? It has to do with how the atoms are structured. It has to do with how the atoms are structured, how many electrons there are. There's a ton of variables involved. You don't need to know all those variables. All you need to know is that different materials, electricity flows either easier through or harder through. Think of it like an asphalt road versus a gravel road. Asphalt's easier to drive on, it's smoother. A gravelly road, your car is going to be harder to go fast on. Different materials, different properties. So resistivity, purely based on what the material is made of. Purely based on how the atoms are arranged. Now, in here you notice that resistivity does depend upon the material and temperature. Why does temperature matter? Well, remember, what is temperature? On a fundamental level, if something is hot, what are those atoms doing? They're wiggling around. And so it's that same idea. So if they're wiggling around, if these atoms are wiggling around, the more they wiggle around, the more likely those electrons are to get smacked by them, knocked the wrong way, and that kind of thing. The slower they are, the easier it is for those electrons to slip through. And so when we look at this equation, we see as temperature goes up, resistivity goes up. As temperature goes up, resistivity goes up. That's what this equation kind of shows us. Yeah?
Does the higher resistivity mean it's easier for electrons?
It's harder. And that's at least nice. If we think of the word resist, we're going to see the word resistance in a bit. These words are very similar. But the higher the resistivity, the more it is resisting. Yeah, that's a great question. The more the resistivity, the slower those are going to move. And we're going to see that when we get to Ohm's law in particular. So that's a good question. Higher resistivity, the slower they move. So if we actually look, let's look at these. So the higher it is, the slower they move. I hope I would say that correctly. The higher it is, the slower they move. Let's look at wood. Hopefully you know that it's a bad idea to build circuits out of wood. The resistivity here, huge. 10 to the 8, 10 to the 11. That's a big number. Let's look at silver. Let's look at copper. This is 1.68 times 10 to the minus 8. That is 16 to 19 orders of magnitude difference in how easily electrons move through it. A 16 to a 19, that is a 1 with 16 zeros after it, times better for electricity. So, makes sense why we build our circuits out of copper instead of wood. And we can see very small differences between silver, copper, gold. Interestingly, gold conducts electricity worse than copper does. Gold conducts electricity worse than copper does. But a fun fact for you all, your phone has gold in its circuitry because gold has the very special property that it does not rust. Gold does not rust, and so when you build it in circuits, you know it's going to always keep doing the same thing. Whereas copper, if it's exposed to the air, look at the Statue of Liberty, believe it's copper. It is not bronze, right?
Copper.
Great, it is copper. Good, wanted to check that. Statue of Liberty is green because it rusted. So, we build circuits out of gold sometimes because they stay pristine. And when you're talking about a phone, you can't be having variable resistances. If it rusts, that resistivity will go up. So, that's resistivity, conceptually, there you go. Why does temperature matter? They wiggle more, there you go. All right. Let's see, how much do I want to show? This is going to be a doozy. I'm going to start the poll, and I will literally solve it for you while it's open, because I honestly don't fully expect you all. Maybe you'll be able to get this. It'll be a good try. Here's the equation. This will be just a good kind of math practice, but I will leave this open and let you correct your answer, because normally clicker questions don't involve math. This one does. So I will solve it with you all and leave it open and let you change your answer. It says, what temperature change is required to double gold's room temperature resistivity? So here's our equation that gets resistivity. It says resistivity equals the resistivity at room temperature times 1 plus alpha. Alpha is just a constant given per material. So this is really just a math problem, just plugging in the variables. It's a plug and chug situation. Times T minus T naught. And I'm going to show you all. You may ask yourself, what exactly should I be using as room temperature? Generally, it's 20 degrees, but I'm going to rewrite this just to make your life a little easier, to show you that you don't even know that. Don't even need to know that. T minus T naught, bam, there's delta T. Final minus initial. So great, you don't even need to know that because it's asking for what is that temperature change required. What do I need to change that temperature to double this? I'll let you kind of play around with it some, see if you can figure it out. I'm not going to spend too long on it. I will solve it in front of you. You'll be able to pick my right answer, 3 points, all that kind of jazz. But kind of play around with the numbers. I believe this question may be similar to one of the ones in the problem sets, and you'll know how to do that as well. Be a good time. But there's a reason for this exercise. There is a reason for it. Yeah.
That goldfish looking thing, an A? Plus?
It's a great question. That is a Greek letter alpha. And alpha is called the temperature coefficient, and again, it's one of those that will give you a problem if you ever need it.
It's a lowercase a.
Yes, it is lowercase Greek letter alpha. Yep. So, looks like an A. It's the first letter in the Greek alphabet as well. If you ever heard the phrase alpha and omega, alpha is the beginning, omega is the end. Alpha is the beginning of the Greek alphabet. Some of our letters look like Greek letters, some of them don't. Our A looks very similar, but it's very slightly different. It does kind of look like a fish, but we kind of usually draw it something like that. So, alpha. All right. So I'm going to go ahead and start. See some responses here. I'm going to start kind of going through it. You can kind of follow along and see what happens. Here's how I'm going to do this, and this is going to maybe throw you all for a loop, but anytime you have an equation and it says, what should I do to double something? We can do a ratio kind of problem. We can start with our original. So our original is going to be P naught times 1 plus alpha times change in T. So that's our original, and at the end of the day, bam, it's just going to equal P naught. That is at room temperature. So our change in temperature in that case would kind of be 0. We want to double it. We want to double, at the end of the day, we want our resistivity to be double. So that's going to equal rho naught times 1 plus alpha times delta T. So honestly, if you kind of look at it at this point, you're going to see something very nice. You see something very nice. All we did is we doubled. We said we want to double it. We want to go from what it was before to double. That's the end result. We want it to be double. Okay? Here's the beauty. There's a rho naught on this side. There's a rho naught on this side. Guess what they do? Gone. Disappeared. They're from both sides. We wanted to double it. Great. Now it's doubled. I put a 2 in front of that side. So 2 equals 1 plus alpha times delta T. At this point, if you want to start plugging in numbers, go for it. We could leave it in terms of variables. I'm just going to opt to put in the numbers just to make it easier to follow what I'm doing. 0034 times delta T. I just have to solve for delta T. I doubled the variable I wanted to, which was my final one. Algebra here gets pretty nice. I subtract over the 1. 2 minus 1 is 1. Times 0.0034 times delta T. Delta T will be 1 over 0.0034. We just plug that into our calculator, and we get our answer. If this did not make sense, again, like the last one with kappa, with the dielectric, I'm literally just doing this problem just to kind of show this equation off. Don't let it stress you. I'm not going to ask a question like on a test. I showed this to you all just because I wanted you to see this equation. I wanted you to see that temperature affects the resistivity. I want you to see that when we get our answer here, we get 294, which means our temperature went up. So the whole point of this equation was to show degree C, 294, and this is again approximate, so my apologies that my answer is slightly off of what that should be. Let's go ahead and just change that to a 4, but that's the closest answer. That's what it's going to be. So my apologies, it was 4 off, but 294 degrees C. Change your answer to that on the clicker. I'll give you all a few seconds to do that. The takeaway from this, resistivity changes with temperature. And you have to heat it up a good amount for that to start changing. What do I have to do to double its resistivity? I have to heat it up by 294 degrees Celsius. This is not Fahrenheit. What is the conversion to Fahrenheit? I have no idea off the top of my head, but you know who does? Google does. So let's convert it to units that maybe we're more familiar with, since we live with freedom units in this country. They're not great. If you haven't been convinced that Celsius and the metric unit is better, maybe I'll get the unit conversions, hopefully, as you're all doing this class. Just imagine, instead of converting from meters to kilometers and just multiplying by that, imagine having to multiply feet to miles and having to, every time you do that conversion, you'd have to divide by 5,280. If you haven't seen how disgusting that is, try it. It's awful. So Celsius to Fahrenheit, that is a 560 degree difference. So if you heat up gold 560 degrees above room temperature, which is quite toasty, if your circuitry is running that hot, you have a problem. You'll double the resistivity. You got to really crank that heat up, though. These things tend to stay pretty constant. Good news for you all. Every problem I'm going to give you, we assume that it stays at a constant temperature. So just, again, keep that in mind, but it is possible to change it with temperature. All right, hopefully everyone's changed their answer. Let's see if there's any lollygaggers. All right, there's 12 of y'all. You got 5. It's still open. If you're one of the 13 people, I can't even pick the right answer. It's that one. It's the one I boxed. 3, 2, 1. All right, I get it. It's near. We're getting near the end of class. You know, maybe you went and took a nap or something. I don't know. Whatever. The rest of us are with us though. So great, we got that down. So that's kind of what we've talked about so far. All right, resistance. We are going to learn about Ohm's law next class. So for now, don't worry about this too much. This V equals IR. Here's what I want you all to see. Resistance. So we talked about resistivity. Resistivity was the material's property to resist. Let's just put a star here. I'm going to not try to box and cover things. Resistivity was based on the material. I said it does not matter how much, it does not matter how big. It was like density. Resistance does. Resistance, it does matter. When you use a wire in a circuit, it matters how big that wire is. Let's again use some analogy that I've used before. Let's think of a road. It's real nice if you pave a road. That's decreasing the resistivity. It's making it smooth, cars can drive nicely on it. But if my road is only a single lane, I still can't fit that many cars on it. How can I make more cars fit on it? Well, how about we make it 4 lanes? We increase the area. We increase the number of lanes on it. If we increase the area, that's on the bottom, we are decreasing the resistivity. If you divide by a number, a bigger number, you get a smaller number. So, we can see that in this equation. We have our resistivity, bam, that's just there. Area is on the bottom because as area goes up, resistance goes down. As area goes up, resistance goes down. As my wire gets fatter and bigger, it's easier to go through. It's a multi-lane highway. As area goes up, resistance goes down. And length. I mean, if it's a long wire, there's more atoms for it to go through. That's basically the gist of it. A long wire, you got more things you got to push it through. As length goes up, resistance goes up. We can see that in our equation. Length is on top, so as that gets bigger, resistance gets bigger. As our area gets bigger, resistance gets smaller. Every material resists electricity. Every material. Now, I say that as with everything in physics, there's always a little asterisk next to that. There's technically something called a superconductor. Superconductors are very, very special materials that if you get them extremely cold, we're talking usually liquid helium temperatures that is 4 degrees Kelvin, 4 degrees above absolute zero, they have no resistance. It is possible to have a wire with zero resistance. Those are very special. They're called superconductors. They're not going to come up in problems in this class. But they're very important. They're how MRIs work. MRIs, we're going to learn eventually, use magnetic fields. How do they make strong magnetic fields? From making a lot of electrons flow really quickly. The only way you can get a lot of electrons to flow really quickly is to make the resistance zero. We'll get to that eventually, so I want to put that little star there. It is technically possible to have a resistance of zero, but it is very hard to do. And the first person to make a resistor that is superconducting at room temperature will probably win the Nobel Prize because it will have drastic effects on society. Currently, all our wires, everything in the walls like copper, it has a very, very low resistance, but it still has one. It still matters. The power lines outside are made of chunky, thick things of wire, especially the high transmission lines. We're talking I'll look it up later. I don't want to spend too much time on it, but it's something pretty significant. Several inches. They report in inches because freedom units. It's a pretty thick wire, a very big area, because when you're transmitting electricity over super long distances, you want to keep that resistance as low as possible. In our case, we'll be talking about pretty small wires. So, conceptually, there you go. Where's the derivation from? There's something called Maxwell's equations. None of us are physics majors in here, so you'll never see this again. But just know that it comes from something called Maxwell's equations, which are foundational equations in physics that describe how charge flows through things in electric fields and magnetic fields. Goodbye. All right. So, yeah, if this was a 2049, if this was a class of engineers and physicists, it would be more relevant because if you're electrical engineers, you will see Maxwell's equations. But none of us are, so I'm not going to waste the time. We've talked about this a bit. Again, hey, ratio problems. We love these. If I double the length and half the diameter, what is the value of its new resistance? Made of the same material, but if I double the length and half the diameter, what is the value of its new resistance? I'm going to give you all some hints, because otherwise, this one's not. So, let's throw that equation up here. I'll be real kind. I'll put that on there. Rho, length over area. This is a circular wire. So here's the thing for you all to remember, and I'll let you kind of put the pieces together. Area for a circle is pi r squared. Area for a circle is pi r squared. So this problem has a little bit more complexity than it may appear at first glance. By half the diameter. So I'll let you think of the relationship between diameter and radius. And if I half the diameter, what does that mean? What am I doing to the radius then? I'll let you think about that. So a few pieces to this puzzle. But we are going to have to be comfortable with this idea of plugging in. Every wire is circular. No one's building square wires out there. So you'll never see a problem with square wire or triangle wire or star wire or trapezoid, whatever. They're all circles. Area is always going to be pi r squared when you do these problems. Circle wires are easy to manufacture. That's just what it comes down to. Circles are really easy. You can kind of just push metal through something, extrude it. So it's an engineering consideration. But every single wire we do in this class, every single resistance and stuff like that, you can assume a circular cross-section. I will usually try to make that explicit, but if you see the word diameter, it's a circle. It's always a circle. Always will be. And I want you all to notice there's a squared there. Remember that squared makes things spicy. So this is kind of, these ratio problems are really good for us to do. Really help us explore the equation. Alright, I'll give you all about, we'll go to 250, so I'll give you about 10 more seconds after this. And we'll investigate this equation. In 5, 4, 3, 2, 1. All right, let's go ahead and do this. So remember, every ratio problem, I'm going to underline these just to make my life a little easier so I can track them. If I double the length and half the diameter, every ratio problem starts off by writing the original. We start off by writing the original. That R is hideous, but it won't let me erase it, so you're going to have to deal with it. Rho L over A. So that's our original. Now, let's go ahead and just put in that pi r squared instead of A. Basically, every time you do these problems, you can put that in instead. It's always circle, always. So if you want, that's the equation you use now forever. What's our new one? What's our new one? All right, so we have our rho. What happens to my length? My length doubles. So I need to put a 2 in front of that length. It doubled. It's twice as big. Bam, 2 in front of that. Done. Okay? Pi, you can't change pi. Ever. It's a constant. Again, there's people out there, gosh, I don't know, they've gotten some crazy number of digits with pi. Is there much use to that? No. I think there's an interesting statement, you can fact check me on this, that I believe NASA only uses up to 9 or 10 decimal places for pi. If that's good enough for NASA, kind of shows you it's probably good enough for anyone. So, 9 or 10 decimal places on a constant's usually pretty good for most anything. And what happens to my radius? If your diameter halves, your radius halves. Here's where you have to be careful though. Whatever happens to the radius needs to be squared. We saw this way at the beginning of class when we saw our electric field and our force equations. We saw it way back then. We saw that when our radius changed, when it was squared on the bottom, whatever we did to it had to change. So this is a good reminder of that. If your variable is squared, whatever you do to it also needs to be squared. In this case, that half needs to be squared. So let me rewrite this a little bit. I'm going to leave that 2 on top. Well, that's not ideal. All right, great. I'm going to go ahead and rewrite this a bit. That r gets squared. My 1/2 gets squared. Just kind of make that maybe a bit more explicit what's happening there. All right, pull everything to the front. Once you've kind of plugged those in, pull everything to the front. I have a 2. I have a 1/1/2 squared. Just pull everything to the front. Try to keep it as simple as possible. And rho L over pi r squared. So at this point, what changed? We just got to calculate that thing in the front. If you really want, you got a calculator, you can use it. This is something we could also do mathematically. So 2 times 1/1/4, keep flip change. I'm going to start to run out of room here. I'm just going to replace this right side at this point. I'm going to wish I could replace this right side at this point, but my eraser doesn't work, so we're stuck with it. I'm going to replace it in a second with r naught, because that's what the value of r naught is. This is this. So, keep flip change. 2/1/4 is the same as 2 times 4 times r naught. 2 times 4 is 8 r naught. Boom. So, a lot of us, I think, just miss that squared. What that squared contributes to it. So this is a good reminder to you all. If you have a variable that's squared and anything happens to it, whatever happens to it also gets squared. Okay? If you have a square and something happens to that variable, whatever you do to it gets squared as well. And I can prove that to you all. I did this last time. If r is 1 and r becomes halved, that means r is now 1/2. Let's just write this over here. So if r was 1, r squared is 1. Okay, pretty straightforward, 1 times 1. So if r is now doubled, 1/2. So if r is now 1/2, r squared is 1/4. 1/2 times 1/2. So that maybe makes it a bit more explicit why that is. Whatever you do to a variable, if it's squared, it needs to square. All right. Do a quick look through, make sure no one's getting anything. Copying stuff down. We have 10 minutes. I think, we'll see how much farther we can get. There's like a couple problems at the end. If I can't do them today, I may just post the solutions. This is not ideal. The writing wants to follow me everywhere I go. So let me just quickly save this as a new file, reopen it, and hope that it goes away. If not, we will figure it out. Sometimes this happens. This is a good point to actually note here as I'm saving this. You all will notice that I upload the files as both a PowerPoint and a PDF. The reason I do that is because all this writing, for whatever reason, takes up a lot of storage, and it also doesn't look the way you would expect. So if you ever want to see exactly what my writing is, I've put the PDF for that exact reason. Please make use of it. It's honestly going to be a bit easier to, it's going to look exactly the way I want it to. Whereas if you open the PowerPoint, sometimes all the formatting can be a bit wonky, and the PowerPoint file itself gets a bit chunky with all the writing in it. Each class I add writing to it, it makes it quite fat. So if you want to quick download the PDF, it will always be quicker, and it will look the way it's supposed to. All right. So all of that, hopefully, yep, it's gone. All right, I'll rewrite it at the end of class. Okay, this is the exact same problem. Not much to say here. So I'll give you a freebie. If I double the length and half the radius, what is the value of this new resistance? This is literally the same problem. Just to prove a point to you all. If you have the diameter, you have the radius. If you have the radius, you have the diameter. So, go ahead. It's like my classic. You all do a lot better than my high schoolers with this, which is what I would expect. You'd be amazed that I'll say that exact same thing. This is the same row as the last one, and then no one shows you who's paying attention. It's one of the joys of teaching college. You all pay attention. It sounds like such a small thing, but it makes teaching so much more enjoyable. Yeah, spot on. If y'all didn't get it yet, I'll wait 10 more seconds. It's that one. It's the one from last one. There are some people that miss it. There always is. That's okay. Make certain you know why. All right, 5 seconds. 5, 4, 3, 2, 1. There we go. Okay, we'll see if we can cram at least one problem in and call it a day. So, yeah, woo, it's the same answer because if you have the radius, you have the diameter. That's the only point I wanted to make with that. Functionally, you may or may not need to know this. It depends how much electronics you're interested in. I'm not going to teach you how to do this, but I just want to show you this is what a resistor looks like in the real world. When you're building a circuit with a resistor, this is what it looks like. It's got these colored bands on it because these things are really itty-bitty on some of the circuits. And so these colors represent numbers. This teaches you how to actually calculate it. Again, if you really want to know how to do this, look at this on your own time. I'm not going to test you on it. So, but it's just a fun little thing. We use the colors because these get really tiny, and if we wrote numbers on it, maybe it'd be hard to read. I don't know. I don't exactly know the exact reason, but that's my best guess. If you're colorblind, it sucks. So it's not the most accessible way of doing these things. And there's probably an argument for changing it just because of that. All right. Okay, let's do a quick problem. And we'll, let's see, is the next one pretty long? Okay, we already did that one basically. All right, what is the radius of a copper wire with a resistance of 50 ohms and a length of 0.5 kilometers? We're just exploring how to use this equation. Just putting all the pieces together. What is the radius of a copper wire with a resistance of 50 ohm and a length of 0.5 meter? Step 1, what is given? The resistivity, I told you I would do this, and I also warned you that the resistivity of copper may change depending on the problem. Because when you look online, for some reason that is the case. 5 different web pages will have the resistivity of copper ranging between 1.68 and 1.72. Why? I don't actually know. I don't know why 5 different websites will say with confidence a value that's different. But at the end of the day, I give it to you in the problem, so that's why you don't have to worry about it anyway. Resistivity is that the resistance is 50 ohms. Ohms is the unit of resistance. I don't know if I specified that before. Let me jump up. If not, this is a very important thing for you all to just keep in mind. I did, but it maybe wasn't super clear there. The unit of resistance is ohms. Why is it ohm? And this is the capital Greek letter. Again, you get to learn the Greek alphabet in physics. Capital Greek letter omega. Why did we use the capital Greek letter omega? It's named after a guy with the last name of the guy who came up with resistance. His name was Ohms. Turns out there's a Greek letter that sounded very similar, so we decided to use it. There's the quick history lesson on that. Again, if you discover something, you get it named after you. And our length, you can use capital L or little l, it does not matter. They're kind of interchangeable, 0.5 kilometers. We need to convert that to meters. So that is going to be 0.5 e to the 3 meters. Okay, what are we solving for? Radius. Remember, every wire we work with is a circular wire. Every single one. There is only one equation for this. R equals rho L over A. You may look at that and be like, there's no radius. But yes, area is pi r squared. So, fairly straightforward plug and chug problem. You're going to see a few of these. Fairly straightforward, just getting used to using this equation. Not too much complexity here. When we get to the next section, there's going to be problems that utilize this, and they're basically a 2-step problem. We'll do a couple of those when we get to it. For now, this section is pretty straightforward. When it comes to the resistance and calculating it, there's not really a complex problem I can give you, with the exception of that temperature nonsense, and we already did that one. So, step 4, plug and chug. I'm going to start doing this more actually at this point. In the beginning of this class, I was putting in the numbers and then kind of doing all the algebra. I'm going to start transitioning to solving for the variable and then plugging in the numbers. Why? Because I think it is a strategy that makes it less likely that you'll make mistakes. If you put in the numbers, every time you write those numbers, it's a chance for you to write that number accidentally wrong. And you may think, I wouldn't write that number wrong. Oh, it's so silly. You'll be, and I say so silly, I do it all the time. you'll write in one step 30, and the next step you accidentally write 3. And then you're just like, oh, that stinks. You're not going to write the variables wrong. The worst I've seen is someone forget to put a squared. So that's why don't forget your squareds, don't forget your squareds, don't forget your squareds. But otherwise, it's pretty rare for people to lose a variable. All right, so we're going to solve for R. Rule of thumb, when you're doing algebra, if the variable you want is on the bottom, you need to get it on top. That's one of the first steps you should try to do. Rule of thumb of algebra, if your variable's on the bottom, we need to get it on top. So let's go ahead and do that. We're going to kick this R squared to the other side. We're going to get it on top. So R squared times R equals rho L over pi. We need to get that R on top. And then at this point, the next steps are pretty simple. Divide the R square root. Another thing you may notice me doing, notation-wise, every step you do with this, you write both sides of the equation. So because of that, I don't want to just keep putting equals, 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 because then it all becomes a big blob. So anytime I do a new algebra step, I put a little arrow. That's just a nice little way to keep things separated, organized, and not just have a train of equal signs. That just becomes a nightmare to read. So R squared equals, we divide the R over R times pi, and then we're going to square root that. And at this point, it's so nice. You just put in the numbers into that, and it's one time into your calculator. The less times you plug things into your calculator, the better. Because every time you plug something into a calculator is an opportunity for you to make a mistake that may be hard to catch. It is very hard to catch if you accidentally plug things into the calculator. I always recommend, let me go ahead and make this a new slide, and I'll tell you what I always recommend after that. So I'm going to write the numbers in there. I'm going to put the numbers in exactly as they should be. And the trick to making certain that what you plug into your calculator is correct is having this final form, plugging it in one time. Okay, so R, I just need to put the numbers in, is the square root of 1.72 e to the minus 8 times the length, which is 0.5 e to the 3, divided by my resistance, which is 50 times pi. Highly recommend just use the pi button on your calculator. If you really want, you can put 3.14. It's just going to change whether your answer is off by like a third decimal place or something. So here's the technique. When I plug it into the calculator, I make certain what I'm plugging in looks identical to that. So I'm constantly looking up and down, checking what I wrote, checking that that's what I put on there. That's the beautiful thing about having one equation at the end. I can just look at my calculator, see, okay, yep, I got square root 1.72 e to the minus 8 times 0.5 e to the 3 divided by 50 times pi, and I can just read off my calculator. It should look identical to that. Depending on your calculator, and a nice thing, depending on your calculator, the graphing ones can be nice because it can show you what it'll look like at the end. The way I plugged it in actually accidentally put the pi up top. You may not, your calculator may not show you that. Again, it depends on the calculator. Some of them do that. So I made a calculator error. It showed me that my equation here did not look like the equation here. I fix it, make certain my pi is on the bottom, and then I get the right answer. So be careful with plugging things into your calculator. As silly as it sounds, it is a skill, and nothing's really going to tell you. Well, the one thing that'll tell you, meters, done. Whether or not you did it right is if it's one of my answers in the test. If not, that may be one of the reasons why that happened. So, there we go, y'all. The last problem was just a temperature one. I'll probably solve it, post it online, but we already did one like it, so no reason to bog us down on it anyway. Thanks for hanging in there. Ask me questions about voltage and potential energy. If you have them, please email me. Conceptually, I've seen this as tying people up. That's expected. That's normal. Voltage and potential energy are tricky like that.